So the thing is, in this class, we're not trying to get the fastest solution. It's more of a direction programming. So now we have a square of 1's. You're given an n by n bitonic array, and the goal is to find the set of elements in the array that form a square with only 1's. So here, we have an array that has both 0's and 1's in it. And we want to find the largest subsquare that contains just 1's. So how do we do this? Well, brute force would be, if I give you an array, how do you tell me if it has all 1's in it? I'm giving you a square array, so that kind of makes your job. Actually, I don't think it matters if I give you a square or a rectangular array. But anyway, yeah.
Look for a 0.
Look for a 0, right? The existence of a single 0 tells me that what I have right now is not an array of 1's. So if you were to define a square of 1's, so a 3 by 3 square of 1's is, if I iterate through all of these and they're all 1's, it's 1. But how can I think about a square recursively? So let's say I have this function is square of ij. Let's say ijk, just for simplicity. That tells me if the subsquare, or the subspace, starting at ij is a square. Okay? So if I know a couple of things, I can start to define a square recursively. Right now, a 3 by 3 square is defined as all I, all j, iterate through all of them, and I have a 3 by 3 square. If I knew that somebody else told me that this was a subsquare, and then I also knew that this was a square of 2's, and then I also knew that this was the square of 2's, if I know that the subsquare starting here is a 2 by 2 subsquare, and I know that the subsquare starting here is a 2 by 2 subsquare, and I know that the subsquare starting here is a 2 by 2 subsquare, and this element is 1, then I know this whole thing is a 3 by 3 subsquare. Does that make sense? So if I know that, let's call this element ij. If I know that the area starting from, I hate how he used the index in J. I goes this way, J goes this way. Right. If I know that the area starting from I comma j plus 1, which is this spot, if I know that this is a 3 by 3 square, and I know that this area over here, which starts from I plus 1, comma j, is a 3 by 3 square, and I know that this area over here, which is, and this index is I plus 1, j plus 1. Is a 3 by 3 square. And A of ij is 1. Then the whole subarray starting at I comma j is a 4 by 4 square. Raise your hands now if you have questions about this. I think the notation I used was really bad, actually. I'm going to change these to S's. So if I want to know if I have a 4x4 square, I check the top left element, and then I see if everything else is 3x3 squares. If you think about this in the smallest case, very trivially, one way of testing the limits of recursive problems is, testing recursive definitions is check the limits of the definition. Check the 0th case and check the largest case possible. So let's check a really, really small case. 1, 1, 1, 1. We would agree that this is a 2x2 square. If this is my ij, this is I comma j plus 1. This is I plus 1 j plus 1. No, this is I plus 1 j, and then this is I plus 1 j plus 1. If the subarray starting at I comma j plus 1 is a square, this is a 1 by 1 square. If the subarray starting at I plus 1 j is a 1 by 1 square, which it is, and if the subarray starting at I plus 1 j plus 1 is also a square, and this is a square, then we know we have a 2x2 square. So we make 3 checks, and we check if the top left element is a 1, and if it is, then we know we have a 2x2 square. Now that we have this sort of intuition about how to define a square recursively, I'm going to change gears a bit and try to think about a few different cases that we could run into. So again, smallest case possible. And I want to quickly label this as I comma j plus 1. This is I plus 1 j plus 1. This is I plus 1 comma j. And this is ij. The question asks for the maximum possible subsquare. So we're going to call that m. Mij will give you the maximum possible subsquare starting at I and j. What is m of I plus I comma j plus 1? So let's be clear. Mij gives you the side length of the largest subsquare of 1's starting at ij. What is mi comma j plus 1? 1. What's m I plus 1 comma j? What's the largest subscore starting from here? 1. What's m I plus 1 j plus 1? Right. The largest subsquare of 1 starting from here has length 0. So then, based on those 3 pieces of information, this one, and this one, what is the size of the largest subsquare starting at ij? We know it's 1, because we can't go further. But how do we sort of use these 3 pieces of information to come up with the fact that the largest subsquare starting at ij is actually 1? This needs, if it was 2, this would need to be 1, this would need to be 1, and this would need to be 1. So how do we use these 3 pieces of information? Yeah?
So you have those 3, and then got the maximum range.
Yeah, so it's the minimum. M already tells you the maximum square sublength starting up. So if I know that the maximum is 1 here, and the maximum is 1 here, and the maximum is 0 here, if I take the minimum of these, that's what tells me the information. So the min of all of these 3 is 0. So since the minimum is 0, if I add 1 to 0, well then I just get 1. So we'll say Mij gives you, or finds, the length of the largest subsquare of 1's starting at ij So Mij finds the length of the largest subsquare of 1. Yeah.
Okay, what if you have 0, 0, 1, 1? Then by doing this,
Let's draw it out.
but then you have 0 plus the min of 1, 1, and 0.
Oh, you also need to check that this is actually 1.
Oh.
Right, that's, if this is 1, and this is a subsquare, and this is a subsquare, and this is a subsquare, right? You can't just, yeah. So Mij finds the length of the largest subsquare starting at the top left-hand corner, pinned at ij. If I know the maximum subsquare starting at I comma j plus 1, and the side length of the maximum subsquare starting at I plus 1 comma j, and the size of the maximum side length starting at I plus 1 comma j plus 1. So in that case, that's basically saying the blue thing, the purple thing, and the red thing are all squares. And ij is also 1. So and a of ij is 1. Well then, I take the minimum of these three things, and then I add 1 to it to account for the fact that I have aij. So that's the general case. Again, if this is a 1, and I plus 1 comma j plus 1 is a 1, I plus 1 comma j plus 1 is of length 2, and I comma j plus 1 is of length 2, and then whatever is also of length 2, then I know I have a square of length 3. If this is 0, then the largest subsquare I can have starting here is 0 automatically. Okay, and then what are some potential, okay, let's start here. The general case of the recurrence, does it make sense? Okay, what are some issues or edge cases I could run into here? Yeah.
Well, if it's like, say you're at like the current index that's not 0, right? But like you still want to explore like look at like the other aspects of subsquares, right? Because they.
Right. So you're saying if I pick this specific ij, and I start my recursion here, well then I wouldn't explore all of the other ij's, which is you do need to do that, and there's a way of handling that. We'll get there. But I mean, in this recurrence itself, what am I missing? It rhymes with smaces. Base cases. So, what are my base cases of this recurrence? So, I'm accessing elements at, where could I run into errors if I access something that's out of bounds? That's only if I and j are out of bounds, which means that if I have something where I have I plus 1 is bigger than n, or sorry, I is bigger than n or j is bigger than n, I've indexed too far out of the array, and then the maximum size of a square that I can have starting outside of my array is 0. So if I is greater than n, or if I is greater than n, or if j is greater than n. So this is my recurrence. So now, he pointed out something interesting. How do I actually call my recurrence to get my answer? If I just call Mij of 1, 1, so if I call m of 1, 1, what's going to happen? What if I call m of 1, 1 here, what will the return value of my function be, based off of the English description I gave you? Who thinks 0? And who thinks 1? 0. Why 0?
Well, because like the ij, the index is just 0, right? So then.
This index here.
Oh, never mind.
No. Go ahead. I want to know what you were thinking there. It's important.
Well, I thought it was the 0.
Mm-hmm.
So then.
Sorry. Yeah.
Yeah.
So if I start Recall the English definition. Mij finds the length of the largest subsquares of 1's starting at ij. If ij is 1, 1, the length of the longest subsquare here is 1. If I start here, the length of the largest subsquare is 1. So how do I actually find my answer? I can't make a single function call and get this answer. If I were to start, if I magically pick this as the right starting point, then I get that this is my optimal square. So where do I start calling this recurrence from? Yeah.
Bottom right.
Okay, so he thinks the bottom right. So let's say I start calling my recurrence from the bottom right.
Or you start filling in the values.
I'm sorry?
You start filling in the values.
You start filling in the values. But if I simply just started, if I just said, hey, I call m of nn, well, what happens in my recurrence? I go out of bounds pretty much immediately. So this isn't going to work. So I agree about your fill ordering, but what is the actual return statement that I need to make at the end of the recurrence? Okay, let's start here. What does Mij tell you? Someone should tell me what Mij tells me.
This square of ij.
The largest square starting at ij. Okay. Where the top left-hand corner is pinpointed at ij. So now do I know where the starting point of my square is going to be? So when I don't know something, what do I do? Try all of them. So to return my actual answer, I have to take the maximum over all I ranges from 0 to n, or sorry, 1 to n, and all j ranging from 1 to n. And I want to take the maximum of Mij. Because literally any of these points could be the starting point of my square, and I won't know unless I try it. So now let's take a look at runtime. How many values are there to pass into I, potentially, in terms of big O? N, okay. How many for j? And then, how long does it take to find the minimum of 3 elements? O of 1. So I have n possibilities. I have order n squared subproblems. Each subproblem takes constant time to evaluate when memoized. So my total runtime is big O of n squared. But I said I was taking the maximum over all of these elements. So am I actually going to make n squared calls to an n squared function? If I have all of these pre-computed, let's say Mij was filled in for all I and n. For all I and all j, Mij was already filled in properly. Finding the maximum value in this array is simply iterating through order n squared elements and just taking the maximum. I'm not saying for I in range 1 to n, for j in range 1 to n, call an n squared function. That's not what I'm trying to do. I'm saying I've already filled this in, and now the table is populated and I'm just finding the maximum value of the table. Let's look at memoization. So what's my fill ordering going to be? M of I depends on mi plus 1. So that means mi plus 1 depends on mi plus 2, which means I plus 3, which means I plus 4, which means I need to have pre-computed the last value I'm going to get first, which means I need to fill in decreasing order of I. So decreasing I, because I depends on I plus 2, which depends on I plus 3, so we want to pre-compute that. And then, what about j? j depends on j plus 1, which depends on j plus 2, and that recursion is going to keep going until I hit j bigger than n, in which case I stop. So I want that to be the first value that I compute, and I want to move backwards. So I'm going to have decreasing j. So I'm going to start here, and then I'm going to go in, let this direction be I, let this direction be j, decreasing I and decreasing j. And what's my space complexity here? Yeah, it should be n squared. Okay, so that's my memoization space complexity. And let's make sure our runtime is consistent. So I told you one way of viewing runtime is how many subproblems do I have, and how long does it take to compute each subproblem. And n squared subproblems, and it takes constant time to check 3 elements. Let's take a look at the memoization table. In order to fill in one element of the memoization table, I need to make comparisons to 3 neighbors. That takes constant time. But I have n squared elements in the table, so n squared times 1 is order n squared. So no matter how we look at it, the runtime is n squared. And at the end of this, I take the maximum over n squared elements. So that's consistent. So we have memoization, we have fill order, we have runtime, and we have space complexity is O of n squared. Okay. So questions about this so far? Now let's say I want to actually return the coordinates of the square. So right now I'm returning just the length of the square. What if I want to actually return the coordinates? How do I do it? Yeah.
As you're filling in the table, you keep track of the max number, and whenever the max number changes, you also keep track of the max number.
Okay, so as I'm filling up in the table, I keep track of the maximum number, and as that max number changes, you just have one variable that says max. That works. Let's say now I want to reduce the amount of space that I have. Do I really need order n squared space to solve this problem?
No.
Why or why not? Yeah.
You only need the previous row and column that you're looking at.
Yes, exactly. So I need the current row that I'm memoizing. Let's take a look at, let's fix just I. I depends on just I or I plus 1. So for a fixed value of ij, let's take this value of ij. I only need to keep track of I, and row I plus 1. So that's order n space, or order 2n you could say. And then for a fixed value of j, I only need to keep track of j and then j plus 1, which means I need to keep track of the current column that I'm filling in, column j, and column j plus 1. And this is order 2n. And then every time I move on to the next row or column, I can just empty one of the 2 arrays and refill it in. So really, at any given point in time, I'm only going to be making accesses to the columns before me or the rows before me. And that too only one row. I need one extra row and one extra column. So at any given point in time, my program needs 4 order n arrays total to run properly. And that's order n complete. So in theory, you could reduce the space complexity of this problem from n squared down to order n. And how would you think about doing this? Let's say you did want to. So I'm computing some ij value, and I have 2 columns here for my i's. I plus 1. And I have, or this is rather j plus 1. And I have 2 columns here, I and I plus 1. Just for example. I move on, I've computed ij, I've computed I plus 1, j plus 1. Now I want to compute, let's say, I comma I plus 1, j plus 1. Let's say hypothetically. Or I plus 2, j plus 2. So that would be this value right here. Well, I depend on the previous row, and I depend on the previous column. So this value will depend on this row and this column, but I need to fill in the new values in this row. I need to fill in, and I don't want to make a new array. I'm done with this I, so what I can do is I can actually store in the previous array, and I can keep switching the pointers to the two arrays. So this is a really important concept in computer science that keeps coming up. I don't know if any of you have heard of double buffering before, but in VGA memory and stuff like that, if any of you have taken 391, this is a really fundamental concept that keeps coming up. So I encourage you to play with that. This level of optimization is not needed for the course. You could stick at O of n squared, and you'd get full points on the problem. But really think about how you can reduce the space complexity of some of these problems. That is all I have for you today.